Hello everyone. So this video is to help with your homework 3. In homework 3, I've made problems that sort of guide you to do this method. And I just wanted to demonstrate it real quickly. So this is to solve for circuits using mesh and nodal analysis. This first problem that we're going to do is going to be for nodal analysis. So feel free to pause the video and copy down this circuit. I'll just be solving in terms of variables. Basically, I'll just be setting up the KCL equations. And yeah, let's get started. So for this method of solving circuits, the first thing that you're going to want to do for nodal analysis is figure out what your nodes are. So I'm going to go ahead and label the nodes. I usually use the convention that v sub 1 or v sub 2, like if the subscript is a number, that it's a source, and if the subscript is a letter, then it's a nodal voltage. So I'll go ahead and do that. So right here, we have a node, VA. Here's another node, VB, and another node, VC, and this is our last node, VD. And if you're struggling with finding nodes, this is a good technique to find nodes. So what you'll do is you start at an element and you just follow a wire. Just keep following the wire. Keep following the wire. Once you hit another element, that's when you cross the wire. So I hit R4, crossing the wire, following. Oh, I hit another element, cross the wire, following the wire, cross the wire, hit another element, following, and another element. So that's how you find nodes if you're struggling with that. If you got homework 1, some of those first problems incorrect, that's how you find nodes. The next thing that I do after I write down all the nodes is that we have to place our ground, because nodal analysis it really only works with absolute voltages. So putting our ground allows these nodal voltages to be sort of absolute, because it's with reference to something that we are calling 0. So I'll put my ground here. The best placement for ground usually is where the most voltage sources are attached. Since these two nodes are only attached to one voltage source, and these two nodes are only attached to one voltage source, it really doesn't matter which one you pick. But I want to pick one that's attached to a voltage source because we know that VD now is 0 because we've grounded it. And VA is now equal to exactly V1 because it's just 0 volts plus a voltage of V1, which is our VA. So once you place your ground, the next thing that you're going to do before you even start solving is to figure out how many equations you will need given this circuit diagram. And the way that you do that, there's a fancy little equation that you can use to figure out the number of equations, and that's going to be the number of nodes minus the number of voltage sources. For nodal analysis, it's the number of voltage sources, not current sources, minus the number of grounds. So in this circuit, we have 1, 2, 3, 4 nodes, minus, we have 2 voltage sources, minus 2, and then minus 1 ground, so minus 1. Sorry if the camera's shaky. It's not the most stable setup. So our total number of equations is going to be 1 equation. And the reason that we do this is that if you're trying to decide if you should use nodal or mesh analysis, you'll figure out the number of equations you'll need for either method, and the one that requires the least amount of equations I would use. I mean, you could do whatever you want. But if it's between like solving 5 equations and 5 unknowns versus 1 equation and 1 unknown, I think I'd rather choose the one that requires only 1 equation. So now that I know how many equations I'm going to use, I'm going to copy down each of these voltage sources. So I'll just put VA equals VB equals VC and VD. And now what I'm going to do, so for this step, I'm going to write these nodal voltages either directly or indirectly to any source that they're attached to. So for VD, I know because it's grounded that VD will be 0 volts. So I'm going to write that down, 0 volts. The ground is usually the easiest one to find. The next thing that I'm going to look at is any nodes that are attached to a voltage source, I should be able to write in terms of another node. So this voltage source V1 is attached to VD and VA. So I can actually write VA as such. So VA is equal to VD plus V1 because it's VD, and then we go up a voltage of V1, which VD we know is 0, so I'm just going to put that as 0. So VA is equal to V1. Then the next voltage that I'll look at is V2. So at source V2, we can see that it's connected to VB and VC. So you can choose either one. I'm going to choose VB just because I want to demonstrate. Actually, I'm going to choose VC in this case, VC. So VC is going to be equal to the other voltage, VB. And here we can tell by the polarity of this source that it's dropping in voltage. So this is going to be minus V2. And now we have our equations. So now this one that we haven't solved for is the one unknown. All the other equations are solved for, except this one is in terms of VB. But if we calculate VB, we know everything about this circuit. So for VB, that's where we're going to write our KCL equation. This actually tells us, this method tells us where we need to write our KCL equation. So write KCL at VB. So this is the node that we're going to write it at, right here. And the law that I like to use is that the sum of the currents into a node is equal to 0. And the way that I write that is like this. And I'll call that I1, I guess. I'll call this I2. And I'll call this I3. So I1 plus I2 plus I3 should be equal to 0. Something weird about I3 that I know just by looking at it, if I write my KCL equations at I3, I don't know the resistance of V2. So what I'll do is I'll just go down the line and I'll look at these branches. So I'll look at these branches, I'll label another current I4 and another current I5. And we know that I3 should be equal to I4 plus I5. So now back down to here, I1 plus I2 plus I4 plus I5 should be equal to 0. And I put that parenthesis just to note that I just plugged in for I3. And this is how we'll write our KCL equations. So for so using V equals IR, our current is equal to, and I'll put a delta V, our current is equal to delta V divided by R. And this is equal to, I guess, V final minus V initial over R. Okay, so let's start with I1. So I1 is right here. And going in this direction, it's going to be written as VD minus VB, final minus initial. I usually just do it in this direction. It really doesn't matter, just as long as you're consistent with the polarity. VD minus VB all over R2 plus VA minus VB over R1, and then plus, so we're going to do I5, VD minus VC divided by R3, and then plus VD minus VC over R4 should be equal to 0. And the next thing that you're going to do is you're just going to plug in for all the things that you know. So for instance, VD goes to 0. So all these go to 0. VC will be VB minus 2. So this one will be VB minus V2. This one will also be VB minus V2. You're just plugging these in. And VA is equal to V1, as we showed before. So now you have an equation that's only in terms of VB. So the next step is just to solve for that voltage at VB. And yeah, that's how you do nodal analysis. I'm not going to show the rest of the steps. I think they're pretty basic. It's just some basic algebra. The most important part is the setup. And really do this in order. Figure out how many equations you need. Write down all your variables because it tells you where to write your KCL equations. And the next question that I'll do, I need to rewrite it again. So actually I have it right here. This is for mesh analysis. So let me just real quick, I'll call this R1, R2, R3, R4, and this one I1 and I2. So for mesh analysis is actually pretty similar to nodal analysis. The first thing, like I did before, instead of labeling my nodal voltages, I'm gonna label my mesh currents. So let me do that. I always use the convention that mesh currents are going in the clockwise direction. The reason I do this is because it's with signs, SIGNs, it's a lot easier to keep track of those. So I'll call this, actually I'm gonna use a lowercase I, IA. This one is IB. And this one is IC. For mesh analysis, we don't have to put a ground. These mesh currents are enough. So the next thing to do after we've labeled our mesh currents is to figure out how many equations we'll need to solve for mesh analysis. This time, it's a little bit different than nodal analysis. So the number of equations is equal to the number of meshes minus the number of current sources. Note that it's for current sources, not voltage sources. And in this case, you can count, we have 1, 2, 3 meshes minus 2 current sources So our number of equations should be equal to 1 again. And then the next step, instead of writing down our nodal voltages, we're going to write down our mesh currents. So just like I did before, IA is equal to IB equals, and IC equals whatever. And here, we can start writing down what we know and what we don't know. So IA, so let's look at IA. So IA, we can tell by the edge current source, so the current source here, that isn't attached to any other mesh, this current, since it's the only current going in this direction, should be exactly equal to IA. So I'm going to write that down. IA is equal to I1. We know that for a fact. Here, for this current source is attached to two different meshes, IC and IB. So what we'll have to do is I2 is sort of like a sum of these mesh currents. So some sort of sum. And the way that I like to think about it is I usually write it in terms of the source current first. So I'll say I2 is equal to, so in this case, IB is going in the direction of I2, so it's going to be a plus IB. And then IC is going opposite the direction of I2, so it will be minus IC. And to get it in terms of IB or IC, I'll just solve for one of them. And it doesn't matter which one you solve for. I'll solve for IC. So IC will equal IB minus I2. So IC equals IB minus our current source I2. So just like before, we have a current that's solved directly and a current that's solved indirectly. And right here, this is where we'll write our KVL equation, so our Kirchhoff voltage law equation. So write KVL here at that mesh. So now we'll do KVL at B, and I usually like to write this title just to bookkeep where I'm writing my mesh currents. I also know the direction that I'm writing my mesh currents in. I always use the convention of writing my mesh currents and doing KVL in the clockwise direction. Again, that just makes signs, SIGNs, a lot easier to manage. Okay, so doing this, so for KVL, it's the sum of the voltages in a loop should be equal to 0. And so what we'll do is we'll use V equals IR for each voltage. So yeah. So one problem though is that we don't know the voltage here. So like if I put a voltage here, V current source, the V current source, we don't know the voltage. We know the current coming through it, but we don't know the voltage. So what we'll have to do is we'll have to use what's called a super mesh, which I'm just gonna do this loop. Doesn't matter, but just as long as the loop includes the mesh IB. Okay. So for this one, I'm gonna put a dot where I'm going to start. So I'll start at this part, and I'll go around the square like that. Okay. So for going from this node to this node, we've got R2, so I usually write it like this, R2 times the mesh currents of, since we're analyzing in this direction, IB is going in the direction we're analyzing, so a positive IB. And the next one is going to be this direction, so that's opposite the direction we're analyzing in. So I will make that a negative IA. And we go around, there's no voltage drop, so we keep going. We've done R2. I'll just put a check by that. Go around, there's no voltage drops until we hit R4. And so now we do plus R4 times, in this case we only have one current source, one mesh current, and it's going in the direction that we're analyzing, so it's going to be plus, so I'll put a little plus IC. Then we keep going, and we get to R3, so plus R3 times, and in this case the mesh current IB is going in the direction that we're analyzing, so it's going to be plus IB. And now we're back to where we started, so that should all equal to 0. And just like the previous problem, we're going to plug into the values that we already know. So we've got R2 times IB, which we don't know, so we'll leave it as IB, minus IA, which is I1, plus R4 times IC, which in this case is IB minus I2, plus R3 times IB. And now we have the equation just in terms of IB. So we only need one equation to solve. And I think you can do the rest on your own to solve for the current IB. Once you solve for the current IB, you know everything. So you know everything about the circuit. You can find whatever voltage you would like across any resistor or any current across any element. So yeah, this should probably make your homework a little bit easier. I just wanted to go over it just because it's a really helpful method. When you have a combined problem, what you'll do is you'll look at both methods first. You won't set anything up. Again, you'll just look at the number of equations that you'll need to solve and pick the analysis method that requires the least amount of equations. All right, that's it from me. Hope you all do well on your homework.